Hi, it's been a whirlwind past year for me. Ended up in a different industry than I ever thought I'd be in. For those of you who know me, I'm now at Anthropic, working on this product, Claude Code. Some of you may have heard of it. If you haven't, hopefully you have heard of it after this talk. Matt Godbold is showing me that he is too much of an addict and is currently using Claude Code on the front row. So that's fun. Anyway, my slides are here if you want to follow along. They are live and they match what's here. So if you have any trouble reading anything on the screen, especially from the back of the room, you can go to the slides and follow along. Here's the nice thumbnail slide, I think, for the conference. So who am I? John introduced me a little bit. I'm a longtime C++ committee member. I have wording or features that are in 17, 20, 23, 26. Almost certainly, it's not officially approved yet, but and likely several of the features I contributed to are going into 29. Here are some of the things that I worked on while I was contributing to the committee. I was the chair of SG9 ranges, which is, I don't want to brag, but among the C++iest of C++ features, you know. I was chair of this conference, got the excellent opportunity to do that, really enjoyed that. I gave these talks called Cute C++ Tricks talks that were really about deep and dark corners of C++. I'm only saying all of this to say I'm one of you. Like, I am C++, and so can you. Like, this has been a big part of my life, and I'm saying all of this to say, now I work in AI. And so if you would have been skeptical of me as an outsider coming in here and talking about AI and talking about the future of coding as I see it, I want to try and convince you with this slide that I'm not an outsider. This is my world, and I really, really appreciate everything this conference has done for my career. And this is not the end of it, to be clear, but I am now working on AI. I am working on coding agents. Let's talk about the elephant in the room very briefly. AI is a bit polarizing right now. I recognize that. I'm not here to talk about that. There are great conferences about the ethics and social impacts of AI. This is a technical conference. I'm happy to talk in the hallway. I'm happy to talk over coffee. But here, I really want to focus on the technical aspects here. I'm not here to convince you that AI coding agents are going to change the way software engineering works, or that vibe coding is the future of software and you should just forget about code quality, or that, like, in general, I'm not here to talk about the social impacts or the environmental impact. Like, I will say up front that I'm very concerned about the environmental impact of AI and of coding agents and of agents in general and of a lot of the aspects of this. And I think for me, like, personally, part of the excuse that the industry is getting right now is that we think that it's going to accelerate clean energy over the next 2 years, but there's a clock on that. And I think a lot of us are going to walk away from the industry if we don't actually see that happening. So this is like, there are a lot of people who very much care about the environmental impact in the industry, and I wish I had more time to talk about that. But I do want to focus on, in this talk, how to help you thrive in a world where you have limited control over how much AI is in the world, right? No one in here really has the ability to stop the advance of AI. You can have opinions on whether or not it should happen, but the reality is, as a software engineer, it's going to impact your life. And I want to do my best to help you thrive in that world. So goals for this presentation. I want to help you understand LLMs at a high level. I want, especially the parts that are really important for writing code, I want you to really have a conceptual framework for how to use coding agents as a tool. I'm going to kind of bounce between coding agents, AI, LLMs, a number of different other terms. The industry is kind of bouncing between these terms also. So it's kind of difficult to, and a lot of them are very loaded with a lot of commercial value to them, and I'm just trying to use them in the technical sense. But I want you to learn how to use them as a tool. I want you to improve your mental model for how LLMs work, how they're trained, and why they make mistakes, so that you can really learn how to anticipate these mistakes and avoid them and really be more efficient in your use of coding agents. And like all of my talks, I really want you to learn how to learn, right? When you see this went wrong and this went right, like I want you to understand how to figure out why this went wrong and why this went right, so that you can improve and iterate and get better, right? And I think that's especially very hard with coding agents. And also, I want to geek out about the future of C++, where coding agents fit into that future, how all of that works, how I think that the language should evolve. You got maybe some of that if you came to the Grill the Committee panel last night. Anyway, I'm going to dive in. I have a lot of material. I'm going to try and not go too fast, but I have a lot of things I really want to say, honestly, because I very much care about this community and I want them to hear all of this cool stuff. All of you, I want you to hear this, not just, yeah, anyway. So yeah, I'm kind of going to frame this in a timeline so you get some idea of the chronology of this, but this is not intended to be an overview of the specific history of AI in the modern world. But it all started with this transformer architecture. This is the basic architecture of large language models used everywhere today. And I'm going to explain this in 3 parts. The first layer that I want to walk through is the input layer. And this is actually probably the most important layer for you to understand as a developer, because this is where most of the things that you have control over are going to be put, right? This is where we turn tokens into vectors. We turn the language into numbers, right? So that the large language model can make predictions based on that. It uses a fixed size vocabulary, and it also uses a fixed context length or context window, right? Those are the 2 important variables here. And it's basically encoding the vocabulary and the position into the context window. And there's ways of doing that encoding that are much more sophisticated now than when this first started, but this was the basic architecture even in the 2017 paper that started all of this off. There's a third thing called the embedding dimension, which you may hear talked about some. That's basically just the dimension that the model is working on, where it's doing all of its transformations. And you don't really need to understand that to use LLMs, but if you hear that, that's what people are talking about. It's like the working dimension. The most important takeaway here, though, is that the context window limits the amount of information that you can give the model to think about at any given time, right? It's the number of tokens you can feed into the model in order to predict the next token. And that basically frames almost everything we build on top of LLMs, especially as engineers that are not directly involved in AI as C++ programmers. Most of what we're going to build on top of AI involves engineering this context window and using it effectively. It is the input layer to the model. So let's talk through, how do we make a chatbot out of just a context window, right? How do we have all of these tokens, right, up here that are just words? How do we turn that into a chatbot? And it's shockingly primitive. We write out like human : and then put whatever you said, and then we put assistant : and that's where we start having the model complete. And when the model feels like it's done completing or answered the question, it says human : and stops. Like, this is literally the text we're feeding in. It's shockingly simple. I think there's a theme throughout this talk that a lot of the technology involved in AI is in its infancy and is in low-hanging fruit territory. We do some sanitizing, because like the first thing people tried to do when they realized this was happening was to like type human : or type assistant : in the prompt and try and confuse it. But basically, this is what's going on right now, and it hasn't changed that much since the dawn of the dawn of the LLM era. But it also means that our conversations get very long very quickly, right? Everything that you've said in that conversation before then is contributing to the context window you're using, which means that's all part of your input. And so as you're trying to craft the input that you give to this model to get the best output you can, you have to think about all of these things being in the context window together, right? Let's talk about transformers. This is my one planned joke of the talk that I bet 5 people in the room will get. Who knows what word goes here? Attention! Yay, we had a few people who knew it. Who gets this joke? How about this one? Okay, makes me laugh anyway. I don't care. The paper is by Vaswani et al. Attention is all you need. But 2 months before that, Charlie Puth came out with a song called Attention. So I like to give him credit. Technically scooped the authors by 2 months. Anyway, the intersection of Charlie Puth fans and LLM engineers is pretty small. It's pretty much just me in the middle. But it makes me laugh every time. So transformers are really the key to modern LLMs. And basically what they're doing is allowing you to build connections between related tokens that could be far from each other in the input. The mathematical structure of this is very interesting. I wish I had time to go into that in this talk. But I don't think the mathematical structure really helps you understand what you need to know to code. What you really need to know to code is that attention is building these connections between things that our brain naturally builds connections between also. So if we have this sentence, the student who had studied diligently for weeks despite the numerous distractions and challenges finally passed the exam. Pretty much everyone in this room can parse that sentence, right? But in 2017, we didn't really have language models that could do that. And it's because they struggled to correlate things that were far apart, right? And the attention is the mechanism that really gives the model the ability to say, oh, student past, that's what's going on here. We're talking about the student. Past is something that pertains to student and not challenges and not distractions, right? And so if you actually look at the attention matrix for the first layer of the model, you can actually see these blocks being higher or larger in magnitude between pairs of tokens that are connected. Now, there's like multiple layers of this model. So once we're past the first layer, right, we're connecting connections, kind of, right? We're connecting a connection to another token, or we're connecting an abstract idea to another abstract idea. And there's many, many, many of these layers. But it starts with connecting words to each other and then connecting those to each other, et cetera, et cetera, et cetera. And it turns out this works unreasonably well. And so there's this third layer that's also important to understand, and actually something that you have a little bit of control over if you're directly querying the API, but not a whole lot, and it doesn't make that much difference. This is how we choose the next token, right? So it runs through this whole prediction thing, this whole mechanism, and it comes up with something that basically turns into a probability distribution of the next token. And then the model chooses the next token based on this distribution. It's called sampling. And usually there's a parameter to the model called the temperature that controls how random the sampling is. Lower temperatures are like more deterministic. It's just going to choose the most likely token most often. Higher temperatures are going to be more creative and more random, but like less consistent. And so it's going to choose something less than the most likely token every now and then. And that is actually really important to accomplishing certain engineering tasks. And figuring out the right temperature in there is just kind of a matter of feel. We don't really have good theoretical understanding of why this is. I think on most models I've seen, the ideal temperature for coding is somewhere between 0.6 and 0.7, but like if you're trying to write poetry, it can be like 0.95 or something. Like it really is just something we play around with and try and figure out. And then this output repeats, right? So we choose one of the tokens, and then we stick it back into the context window and try again. And the machinery will have what's called a stop sequence, which in the case of a chatbot is this like new line, then human colon, right? And when it sees the model generate that, it will stop doing this feedback loop and send you the result. And so we have what are predefined stop sequences that allow us to build this into real infrastructure that happens in the cloud and then sends you back your results. So let's talk a little bit about how training works. And to be very clear, I think there's this perception that that LLMs are just fancy autocompletes that are just predicting the next token. And that's mechanically what's happening, but I don't think it's a very interesting thing to say. And I want to kind of illustrate that mechanically that's what's happening or I want to illustrate how dated that understanding is by talking about how long we've been able to just predict the next token for these things. This goes all the way back to 2018. We were doing pre-training on the same, not on the same scale, but basically with more or less the same technology that we do pre-training today. And you basically start with your whole model with a whole bunch of random weights. And you look at some tokens from training data, right? So here in the training data, this would be back, right? We all know C++ well enough. And throughout this talk, I'm going to use this little set of 3 thinking emojis to indicate the spot where I'm talking about the LLM being at. I couldn't come up with anything better for the presentation. So if you see that over and over again and you're confused, that's what's going on. I'm talking about, in this code snippet, this is where the LLM is at that particular moment. And so here, early on in the training, you might get something like this out of your random weights. You might get 35% back, 11% front, 5% pull, right? And then what you're going to do is you're going to compute a gradient that will cause, of the weights, that will cause the back to become more likely, and it'll cause front and pull to be less likely. The math behind that is a little bit complicated, but it's actually not too bad. And it's something that's pretty understandable. Back propagation is involved in this process. Yeah, and so then we adjust the weights and we repeat. And we do this over and over and over again for very large corpuses of data. We move on to the next token and then try and do that. We do this for a whole bunch of different tokens at once. And it takes an enormous amount of time, an enormous amount of compute to train these things. So that was 2018. That's what pre-training looked like in 2018, and it has not changed much since then. The scale has gone up a lot. But the general idea for pre-training specifically, not talking about reinforcement learning, talking specifically about pre-training, hasn't changed that much since that era. I'm sure someone in the YouTube comments who is an expert on pre-training will correct me. But for the purposes of a C++ conference, that's what you really need to understand about how the pre-training happens. What we started to see as we started to grow these things is emergent behaviors that were surprisingly good. Unreasonably effective is another way to say this. So in 2019, we had GPT-2, which was 1.5 billion parameters and was trained on about 40 gigabytes of training data. GPT-3 was trained on about 570 gigabytes of training data with 175 billion parameters. In a very vague sense, if you look at these kinds of numbers, you can see that pre-training kind of constitutes a compression on the data, right? It's like a approximate compression in a way that allows you to reproduce those tokens, right? It allows the model to regurgitate those tokens in a probabilistic way, but we're compressing the training data into the weights. The surprising thing, and we don't fully understand this as an industry yet, but the surprising thing appears to be, is that it appears that this compression is something similar to what our brains use, this conceptual generalization compression of the data. So that you can, based on one concept over here and another concept over here, generalize to a prediction of a token that's likely to match the input data. This is a metaphor. It's not exactly what's going on. If we knew exactly what was going on, I think I would be giving a talk at an AI conference. And honestly, we don't as an industry. But this is more or less why we kind of think that this is working so well. And when we ask it to decompress the data on some prompt that it hasn't seen in its training data, it uses conceptual generalization in much the same way that humans do. So let's consider this code snippet, right? This C++, right? We have a widget factory. We are taking some sort of default initialized foo factory, and this is a well-known C++ factory pattern, right? It's actually quite an old pattern. I don't see it a lot in more modern code, but we're making a unique pointer, we're calling initialize, and then we're returning, and like, let's imagine that the model is completing right here, right? And there are several completion candidates, right? The obvious one is just widget, but there's no reason inherently, without any special knowledge, that it couldn't be foo or null pointer or, well, what about std move of widget? Is that actually the right? Maybe now we're not sure, right? Like, or std move of foo. I think we're pretty sure it's not that, but we could make a new unique pointer to a widget, but we have, you know, some intuition. It could be a semicolon. It could be 42. It could be an emoji, right? Like this could be, the completion of this could be any token. How do we pick between these things, right? And I want to think through how your brain is doing this, because it's actually surprisingly analogous to how we think that LLMs are doing this. So probably the first thing we're going to do is like, I think the return value is probably going to be ASCII. You can eliminate the emoji. We look at the return type, right? So we are doing some sort of attention correlation in our brain between this token and this token, right? Or this sequence of tokens and this token. And we're like, these two things are probably related in some way, right? And so we're like, int and void probably are not candidates, right? Because these things are not related to that correlation, right? So can you kind of picture in your brain this process of the attention mechanism connecting pieces of this code? If you are a very good C++ programmer, you might have immediately said, oh, foo has been moved. So I can correlate this token here, or this token sequence here, with this token here and say, probably it's not foo or anything related to foo, right? That's a use after move. We have a conceptual picture in our brain that, or conceptual compression of the information in our brain that represents use after move is bad, right? Or I hope you do. If you're at CppCon, and I hope you are getting that idea, right? We know that this factory pattern is probably going to return something that's been initialized, right? So no pointer seems pretty unlikely. So we can cross that off our list. We probably wouldn't initialize something and then throw it away. So like this make unique seems pretty unlikely, right? And probably the variable name is going to be like widget. So even if this were like widget and then we were using foo and you didn't know about use after move, probably the fact that someone had named the same thing as the factory function means that you're probably returning that thing. But now we're down to two candidates. And I bet we have the full spectrum of probability distributions for this completion in the room. Because I bet there are people who are 100% sure this is a move. And I bet there are people who are 100% sure this isn't. I will confess, even with all my years on the committee, my distribution is about this, 93%, 7%. And that was before I looked this up. But like, I'm not sure I could have told you why. We could also do this completion, right? This is actually an implicit move. And so the correct answer is widget. Correct answer. It's not incorrect necessarily to do move, although most linters will probably tell you that you're doing an unnecessary move into return value. This is an implicit move because the type of widget exactly matches the type of the return value. And I'm curious as to what people's probability distributions for this completion is. I think mine looked probably something like this, to my shame as a C++ committee member, especially given I was literally there for this. But yeah, I don't know. Anyone want to shout out the right answer? It is not 17. It is 11. This has always been a part of move semantics. In 14, we relaxed it so that this could be convertible. I think we did some further relaxations in 20. Yeah, there are committee members around here, walking around here, who can tell you a lot more about this. You know, go buy Barry a drink. So, fun thing about working in an AI company is that I can actually go and pick the model's brain on this. Right? I can actually go and do this completion and figure out what its probability distribution is. And this is not something we typically expose en masse to the public, but got permission to share this with you all, so I'm pretty excited. So we feed this into the model, and we get its token distribution. I did this with a temperature of 1.0, which is like the most random, pretty much, that it can get. So this is like not something you would really use for coding, but I wanted to be able to see like if there's any like probability that it's getting it wrong. With small examples, modern models get these things right pretty often. But this is also, I think, most people in the room would agree, this is a pretty dark corner of C++, right? This is not C++ 101, and I don't think most C++ 101 entry-level students would get this correct. So this is not, it's a really interesting thing. And what we see here is something really interesting. And this was a late night at the office when I saw this, trying to figure it out and understand it. And what we actually see is, so on the far right, we have some very small models. This is a model from 2024. This is late 2024, and these are both the smaller versions of our models, Haiku. This is 3.7 Sonnet, which was released in February, slightly larger model. This is Sonnet 4, which was May of this year, and this is Opus 4.1, which is in August and much larger. Yes, we're hilarious, Opus, Sonnet, Haiku. And the interesting thing here is that it seems to be getting less likely to get the right answer in the newer models, right? I did change the variable from widget to var because I didn't really want to bias towards anything specific. And I put a using namespace stood in here so that I would like be more likely to get the move directly, and just try and really sample this very specific issue of, is it a move or not, implicit move or not. And the newer models are still going to, like at a reasonable coding temperature, pretty much always going to do this return correctly. But it was surprising to me that the older models were doing it more often. And I think we have an explanation. I had a lot of researchers and interp folks weigh in on this and help me with this, and I'm really grateful to all of them. But what we think is happening is that the old model just thinks this is Python. And once we start getting towards the newer models, it actually understands move semantics and it has to do a split second and be like, wait a second. 9% of the time, it's going to forget that implicit move is a thing. And just to be safe, it's going to move. So it has a concept of implicit move in its brain somewhere, but sometimes it's forgetting about it, or it's forming that concept too late in the residuals, too late in the layers, and it can't really connect that concept to the return value in order to predict the token correctly, right? And it's still pretty low, right? At temperature of 1, it's 9%. It's still, or 11%. You have to add these two together, right? Because sometimes it's generating the the non-ADL call, which is actually what we would like it to do. But here it is on a log scale, just so you can get some idea that like even the semicolon, the completely wrong answer, has a 10 to the minus 5 probability at temperature 1, right? Which doesn't sound like much until you realize you're generating, 200,000 tokens per day. This is going to happen like once a day in a typical coding workflow. It's going to do something completely wrong. And so this is very hard to get under control, right? You have to be very clever with how you engineer the way the model can correct its mistakes. And we're going to talk about that in a little bit. But the interesting thing here is if I'm correct about this theory that the model understands implicit move, but is just forgetting about it, then we should be able to put a comment here that says this is an implicit move, remind it that implicit move exists, and then this probability distribution should go back to all of the models saying 1. Again, the ones that still thought this was Python code are just going to still not know what moves are. But the newer ones that actually understand the concept of move and are just forgetting about it 10% of the time are going to go back to 100%. And don't you love it when things actually do work? We get basically 100%. There's a little bit of artifact here in the newest model, and we think that's potentially related to the model just trying to be safe because it knows that it won't fail. There's other things there, but this is basically never going to get the wrong thing in real coding scenarios. Well, I say basically never. Obviously, it's a finite percentage at temperature of 1. Some of this is probably just don't code at a temperature of 1. But we can further figure this out. We can further understand what the model is thinking with a really interesting experiment, like how well does it really understand what's going on here? We can tell it that implicit move is broken in our compiler. So is it just picking up on move and being like, oh, I should move? Like, obviously, if it didn't really understand the idea of implicit move, then it would probably try and correlate move here with like the return value and like be more likely to do the move, right? Instead of trusting the implicit move. But if it really understands what implicit move is, it should be able to look at this comment, build up a concept of, oh, I need to do something that I wouldn't normally have to do for implicit move, and change what it generates here. And that actually works, which is really cool. You can see our old models that think they're writing Python still just want to return the variable by itself. They are starting to kind of like be like, oh, maybe I should do something related to move. So it's not like that the old models know nothing about C++, but the new models know a surprising amount. We actually think here, this is the model not believing you that implicit move is broken, because I have never seen this broken in a compiler. But it's still like getting the right answer in this bizarre scenario that is obviously not in its training data, right? This is not a scenario that I've ever seen as a C++ programmer. I've seen a lot of other broken things, but I haven't seen this specific one broken. And yet, the compiler is not just regurgitating its training data. This is almost entirely from its pre-training data, and it's not regurgitating its training data. It's conceptually generalizing about what broken implicit move means. And I think that's really interesting. And here's the log scale just for completeness. Just for fun, threw this one in. And I thought it was very interesting that the newer models are getting better. 3.7 Sonnet seems pretty confused. I think the older models here just vaguely know that move is somehow related to C++11. And so it's like, oh, it's a move, C++11 thingies. And there was, in fact, a fix to implicit move semantics via a core working group issue in C++14 that makes this a little more nuanced, and I'm wondering if that's what it's picking up on. But I think that's very interesting. So yeah, takeaway from this section that I want you to get is that compression through conceptual generalization is a useful metaphor for understanding how pre-trained models store and regurgitate information, right? It is still regurgitating information, and I'm going to talk about why I use that term in a second, but it is regurgitating it conceptually, right? It is thinking about what is going on in conceptually and then generating the tokens that match that concept. Let's talk about reinforcement learning now, which is basically everything that is advanced since 2002. Aside from this, there's been some scale changes too since then, but a lot of the advancements that have really led us into the more modern era, and by more modern era, I mean like since the release of ChatGPT. I still wouldn't even call that the modern era. We'll talk about the modern era soon. But most of that has come from reinforcement learning. And so the problem with pre-trained models is that they really are a glorified autocomplete. This is a conceptual generalization here, but it's like it's predicting the next token, and it's not accomplishing a task, right? The task here is to answer the question, and it is predicting the next token based on parts of the question, but not based on its understanding of this as a task, right? And so this would be a completely reasonable regurgitation of the training data. Std vector size is defined in the standard library. Vectors are sequence containers that represent arrays that can change size, et cetera, et cetera, et cetera. This is an example. Claude wrote all my slides, by the way, in case you're curious, or helped with most of them. I prompted it, but so give me a little credit. But yeah, I mean, this is I gave it an example from a different talk that was not related to C++ and said, generate something that is like this example, but for C++. I think it did a pretty good job. I think that's really pretty cool. But so let's talk a little bit about how reinforcement learning works. This is the part I have to be the most careful about because most reinforcement learning work that's going on right now is very trade secret and protected very carefully. And this is like a very active area of research. But the basic idea is that you give the model a question or a task, and then you generate hundreds of completions for that task. And then you need some way to score those completions. So like you can give it a high school math test that's multiple choice, right? And that's a really easy version of this because you know the right answer. And there's not a lot of ambiguity. If it gets the wrong answer, you don't give it any credit. And if it gets the right answer, you give it a lot of credit. But what if it's generating C++ code? Well, this is actually quite complicated in that, like, you know, some examples from C++ code, if you asked it to generate a function that, you know, takes a random access range, in certain contexts, it might be correct to use FINE there because maybe you don't have C++ 20 yet. Like, it doesn't have the contextual information to know whether or not it has C++ 20. If you want to give it at least a little bit of credit. But like figuring out how to write these metrics, these scoring functions, is an art. And it's not something we've really figured out as an industry. And there's even more nuance to it than that I won't get into for this talk because you don't actually even know which sets of tokens to apply the scoring function to. Sometimes the agent may have taken a wrong turn, figured out that it was the wrong turn, and then taken the right turn. And you don't want to apply your scoring metric to the part where it took the wrong turn, only the part where it took the right turn. And that's an absolute nightmare and active area of research. And then you basically compute a gradient of the weights based on those token completions that makes the model more likely to give the completions with higher scores and less likely to give the completions with lower scores. I'm doing a lot of hand waving here, but that's more or less what goes on. You repeat this many, many times for many, many tasks. Again, enormous amount of compute done. And it's not like these tasks are often short time horizon tasks. You may be doing this for like the task in some of our training Okay, the task in some public versions of training data that I can talk about is often to take a issue from a GitHub repository and produce a fix. And the scoring function is the human-generated pull request that fixed that issue, right? Like these are real-world tasks that we are often training these things on, that the industry is often training these things on. I'm making no comment on what Anthropic specifically is doing. Sorry for that. I really love my job. This sounds really hard. It's a lot harder than it sounds. And I wish I had a lot more time to get into this. I actually had some really great slides about C++ examples of this that I had to cut for time. But let's jump a little bit more into the even more modern era of tool use and agents. So sometime around 2023, 2024, we realized that like XML or JSON, other structured markup languages are just texts. And so we could give the LLM a like description of what would happen if it uses the schema and give it a schema. And then when we see it generate that, we stop, we do the thing, make the thing that we told it would happen, and then give it back the output, and then let it keep completing. So for instance, we could have it run a command in the terminal, or run the compiler, run a debugger, run the profiler, search the internet, search the code in a repository, edit a file. Like I don't think I realized until I got to working in this field that like edit a file is something that we discovered. Like that's pretty crazy to me. So I actually have some of the tool calls from Claude Code using the Anthropic API at least for the edit tool call. So this is like, for now, most use XML. There's kind of a shift towards JSON for various technical reasons I won't get into. But here's what an edit tool call looks like in Claude Code. And Claude has to generate this verbatim in order to change just a few characters in the file. If the old string is wrong, the tool call fails. If there are multiple old strings in the file, the tool call fails. Like, we are in the ED era of agentic tooling. Who here has used ED before? Right. Okay. If you didn't raise your hand, think about it like it's the reason VI is called visual. Because you can't see what you're doing at all in ED. Yeah, it is find and replace. And this is the only tool. Everything you've ever used involving a large language model editing code does this, which blows my mind. There's so many things you have to remember. I would call this superhuman intelligence to some extent, right? Like, I could not do this. I could not do this by myself every time I needed to edit something and ever produce coherent code in a reasonable time span. So I think that, like, the point I'm trying to make here is that the tools that we have are holding us back. I think at some point we will figure out how to create whatever the agentic equivalent of VI is. Spoiler alert, it's not VI, we've tried. It's not Emacs either. But something that provides the same kind of active feedback to the model while it's editing. So it doesn't have to verbatim replace. To give you some idea of how good this is and how good the models are at this. Remember I said Claude Code writes all my slides. I do my slides in JavaScript framework that I forked off of reveal.js back in 2018 because I'm a speaker and do a lot of speaking, and Other speakers in the room know exactly what I'm talking about. Anyway, it's something that you would not expect to be in pre-training data, at the very least. I have it edit the slides. I tell it what I want it to say, and I have it edit the slides. And so I had it generate the edit to my file that added this code block. And this is what that edit tool call looked like. And it got this first try. Here it is, like finding the list item that it needs to put it underneath and adding the code fragment and the tool use that's nested inside the other tool use that it doesn't mess up at all. Like, this is remarkable to me, but this is also, like, to me, a sign of just how much our tool design is holding back the models right now. There's a lot of work actively going into this, but I expect this to evolve a lot over the next few years. I think we really are in the low-hanging fruit era of agentic tooling. Let's talk about reasoning for a minute. I've actually heard a few people mischaracterize this as more complicated than it is already this conference. So basically what started happening is context windows grew very rapidly, especially during 2023 to 2024. I actually gave a practice version of this talk, and I thought I had the wrong number here. I said, surely this is not GPT-4, this is GPT-3, only had 8,000 tokens in the initial release, but it is actually, in fact, GPT-4. There was a GPT-4 turbo model that had 128K tokens, which is a little bit more modern. Claude 3 had 200K tokens. Gemini had 1 million tokens. Claude 4 had 200K tokens. Basically, over the course of 2025, we've seen this level out a little bit. And there are various reasons for that I could go into. Love to geek out about offline. But more or less, context windows are not growing rapidly like they were during 2024, 2023. But in 2024, we were asking, what do we do with all these extra tokens? Here's a log plot of that growth. There was some experimentation early in 2025 with some 10 million token context windows. I think the general consensus is that they're not very useful. When you spread the model that thin, it kind of starts to get pretty dumb. And so we're leveling out mostly in this regime. Look at where this stops in like April. And so what do we do with all these tokens, right? We have all this extra context window. One option that we started with in 2023 is what's called retrieval augmented generation, where you just pull in a document, you pull in a web page, you pull in a bunch of information directly, which to some extent you can kind of squint at and be like, oh, that's an early form of a tool call. 2024, we started doing kind of deterministic tool calls where the model goes and runs the compiler and gets the output of the compiler, right? And that really is starting to use up the window. But close to the end of 2024, people said, wait a second, what if we just ask the LLM to put more relevant tokens in its context for us? So this is literally the entire innovation here from the paper that discovered this innovation. Before we were doing this, where we were like, okay, we're going to start the model completing right after the assistant colon, right? And after, we were doing this. We're going to start the model completing after assistant colon, let me think through this step by step, colon. That's it. That's the entire innovation that shook the AI world in the end of 2024. It's insane. This is, to me, unbelievable that this was something that completely changed LLMs. And we actually, we don't understand a lot of these things. This one's one that I think we understand pretty well why this works. So going back to this architecture diagram that we had earlier, right? We have this transformer layer 1, we have layer 2, et cetera, et cetera, et cetera. And this ... is doing a lot of work. There's a lot of these layers, right? Remember how I said that attention in the first layer is really connecting one token to another token, connecting tokens to each other, et cetera. And then, like the next layer, you're kind of connecting pairs of tokens or connecting connections, right? Later on in the layers, you're eventually building up something that more or less represents an abstract idea, abstraction, right? And that abstraction can then get connected to another abstraction. But at some point, if you form the abstraction too late in the layers, then there's not enough time for the attention mechanism to connect that one abstraction to another abstraction, right? And so it kind of misses the connection and generates the wrong token. But if we tell the model somewhere that it has to, like, first write out some tokens that represent its thinking, quote unquote, it's actually having to take some of those middle layer or late layer abstractions and turn them back into tokens. And because it's turning that abstraction back into a token, and we're putting that back into the context window, we now have a more compact representation of that abstraction, which allows it to be formed in an earlier layer of the model. Does that make sense? I think that's actually a really profound insight as to how these models are forming connections between things. When somebody told me that inside Anthropic, I just went home with my jaw open. I was like, this makes so much more sense now, right? We're moving abstractions into the token layer. So yeah, with that, let's talk about agents. Agents are the big buzzword of 2025. And I'm not talking about the buzzword version. I am really talking about the technical version of agents here. And how they really impact how you use LLMs for coding. Early LLMs, very small context windows, only do relatively short time horizon tasks. Chatbots kind of worked fine with this because, like, even if you're having a conversation with a human and, like, the model forgets something that you said 3 questions ago or 4 questions ago, or the human forgets something you said 3 or 4 questions ago, you're like, oh, that seems like a reasonable thing a human could forget, right? They kind of worked, right? Like, we also use these for fancy inline completions of code, right? Those whole, like, multi-line completions. That's like a very direct application, right? You're just predicting the next token likelihood and then throwing everything away, right? And if the user hits tab, then you stick it in there. And if they don't, then you don't. And you don't have this long conversation history that you have to worry about. So this all worked pretty well. But if you gave it a much more long time horizon task, the LLM would go off the rails pretty quickly. It had pretty limited ability to correct. We were missing this extended thinking piece also. As LLMs got larger and reinforcement learning got better, longer running tasks became more feasible. The key insight was that if we let the model see the results of its actions and then iterate on that feedback, then we can keep the human out of the loop for a little bit longer and have it use up a little bit more time in order to give the user a better response, right? So for instance, if we ask the model to generate code, then give the model a tool to run the compiler on the code it generated, and then add those results of the compilation to the context window, and then ask it to fix the compilation errors, right? So we have this now loop where it can then now recompile the code, see more compilation errors, and it doesn't, like, confidently state that the code that is generated is correct. It actually can check itself, right? And this feedback loop is what really transforms a chatbot into an agent. When people talk about agents, they're usually talking about some form of autonomy with tool use that has a feedback loop that involves some sort of consequences of its actions, results of its actions that it can then use to create better versions of those actions. So this is one of the observations that one of the AI Research Institute's Meter has done recently is that the length of tasks AI can do is doubling roughly every 7 months, and that's held since about 2019. in a very vague sense. I think it'll be very interesting to see what this looks like in 2026 if this trend continues. It's actually accelerating just a little bit if you look at it. I don't know that it'll continue to accelerate, but basically, yeah, I mean, we're starting to talk about models that can run for 24 hours, models that can run for a week, right? What does that look like? What does it look like to write up a task with enough detail for the model to go work on it for a week, and you come back and get a pull request? And is that week of work worth the improvement over, 5 hours of work? It's going to be very interesting. Like, I don't think anyone can predict the future right now. I am an optimist in general, for those of you who know me, but I think it'll be very interesting. So how do agents understand a 1 million line code base, right? From just a few 100,000 tokens of context? And again, I think it's very helpful to ask, how do humans do this, right? How does an agent go through and figure out what's going on in the code base in order to perform a task when it can't fit all of this code into context? And we don't do that either. No one here has the entirety of the Clang code base memorized, right? We search for key entry points. We read through some of the code in those entry points, kind of skim, looking for like relevant things to what we're trying to understand. We look at key types and data structures. If there's a specific piece of functionality, we probably search for key strings or something like that. We might search through the documentation also and then use that to figure out what file we need to start reading, right? In other words, we only load part of the code into our context window, right? And maybe we load like a summary of the rest of the code, or maybe we load like a conceptual picture that might be slightly wrong but good enough into our memory based on like our experience with the code in the past or our experience in analogous situations. Agents do this also, right? So this is a demo that I did 3 months ago at ACCU. And this was with an older model. Our models have gotten better since then. But I asked it basically to go through the Clang code base. So this is Claude Code. I went and initialized it. And I'm going to go ask it to explain to me how const for if is implemented in Clang. Who here has written code in Clang before, like in the actual compiler? These are the people you need to come ask how hard this is. It is very hard. I have done this a very little bit, and it is a very large, very complex code base. And so I'm asking it, how is if const for implemented? Whoops. Spoiler, I'm bringing up someone to do a demo. And it's going to go off, and it's going to go search some things. It actually asks a subagent to go summarize for it. It searches for a lot of key strings. It reads some files, and it comes up with this report. And I'm not going to go through this for time purposes. You can go look at my walk through it in my ACCU talk. But it comes up with more or less a correct description. And so then I go in here and I can say, okay, now I'd like to implement switch const for, right? Which it's going to conceptually generalize based on the conversation about if const for. I am using this as a tool. I am preparing the context with an analogous example that I've asked it to go read about. And then I'm going to give it a task that is related while it still has that information in its context window. And so it's going to go through and write a plan. I'm not going to go through this whole thing, but my favorite part of this whole thing is I asked it to rate the difficulty of this on a scale of 1 to 10, and that is not what I wanted to do. And it says right here that the most difficult part on a scale of 1 to 10 is a 9 out of 10 is convincing the C++ committee to accept the proposal. I think that's a little low. But it has not been to a committee meeting, in fairness, because our notes are not in its training data. They're not public, so, All right, I'm going to bring up Mark Williamson from Undo, who has been doing a lot of agentic work. And we're going to do a quick demo here. Is your mic on?
Hopefully. Am I making noises?
And we started talking back in April at ACCU, right? And you work on a time-traveling debugger.
That's right.
You want to explain what that is really briefly?
Sure. So, hi, I'm Mark. I'm CTO at Undo. What we mean when we say a time travel debugger is the capability to capture the entire execution of a program. So that's actually a machine instruction precision with everything that was in memory, so every variable, piece of state, line of code, and then replay it deterministically. We actually do a load of tricks to make that a lot more efficient than it sounds. We just capture non-deterministic inputs that can affect behavior. But the ultimate goal is that a human or an AI can retrieve any information they want about how that run of the software behaved.
And so you have been working behind the scenes with the Claude Code team a little bit, mostly on your own because we haven't been as good at communicating as we should have been. I'm sorry. But building a tool for our agent, basically a tool, an MCP server, but
yes,
it's a fancy way of creating tools. And the agent now can control the debugger, right? Claude Code can control your debugger.
Right.
And you're going to show us something that you can do with that.
Yeah, sure. So a bit of preamble before we dive in. What I've done in this case is I've played a little game of Doom. I'm using Chocolate Doom, the open source clone that stays quite close to the original source code structure. And I played through this, recording with our live recorder tool. And so I've captured everything that happened, and we can recompute anything that went on in my playthrough. What we've got here is I've run to the end of that recording in our debugger. On the top right, you can see a live update of the frame buffer for the point in the recording that we're currently examining. What I'm going to do now is use our AI integration to find out some high-level information about the semantics of the code. So when was the second zombie killed in this playthrough? What it's doing is invoking Claude Code in the background, and it's handing over the controls of our debugger to Claude. So now it's Claude's job, using specially crafted tools, to solve this. Off we go. It's getting a backtrace at the end of the recording to figure out where it is first, and then it's going to go and do some exploration. And it's kind of like the exploration a human would do. So you can look, and you can see it's found this variable total kills. That sounds like what we want as a clue for how many kills have happened, but it turns out it's a red herring. If you look here, we've run right back to the menu screen. This is part of the initialization of this level. It's the number of kills you can have in the level once it's spawned all of the monsters. So that's not right. It pokes around in the source again, finds the players array, and each player has a kill count, which sounds promising. So then it starts poking around with that, runs backwards in time, and finds when it was changed. And on this occasion, it's found the first kill. It's bookmarked it, so it will be able to come back to it later during its reasoning, and so will the human if you want to check. It's now run backwards again from there to try and find when it was 2. That doesn't work. That's fine. It can recover. It's got a deterministic recording, and it knows how to use the tools. So now it's gone back to the end of time, and it's having another go, and it's trying different expressions it can evaluate to figure out where this kill count became too precisely. You can see I got stuck in the map and menu system for a bit because I forgot all the keyboard shortcuts. Here we go, going backwards, and it's now printing out the kill count, says it's kill count 2, and now it's winding back to find out exactly when that was first assigned, and it's happy. Perfect. This is where the second kill occurred. So it's now bookmarked that, because that's interesting to the user and to further exploration, and being a good little agent, is actually gathering us some additional context we might want to understand what happened. So we're querying out here what time it was in terms of game ticks. We're querying out where this happened in the level. This is all going to form part of its final reporting.
Oh, and this is my favorite part that I forgot to stop you at, is that it did not find a zombie.
Exactly.
It found a possessed. It found that the enum for a zombie is possessed.
Exactly, yes.
And it figured out that possessed is kind of like a zombie. That's probably what Mark means here.
Precisely. So it's kind of generalized from my concept to the real in-code concept it needs to answer my question. So it's confirmed it's a zombie man, and now it's checking where the bookmarks are so it can jump around and provide a good summary for me. One thing I really liked, there's no prompting that's telling it needs to do this. It's decided I might want the previous kill as a comparison point. So it actually jumps back to there in time and gathers some coordinates and other information there. And then we get this final report, which summarizes the answer to my question. You can see we're 18.09 seconds into level based on game ticks. We've got coordinates. We've got a confirmation of the monster type. We've got some information about the previous kill for comparison. And it's cast just a little bit of shade on my playing style by saying this is one of the weakest enemies in the game.
So yeah, thank you for that.
Thank you very much.
This is, I think, pretty, what do you all think? I think that's a pretty incredible demo. And this is all built using just prompting. I don't want to say just prompting because you spent, what, 3 months on it, connecting, teaching the compiler how to, teaching the model how to use your tool, and figuring out what sets of tools it can use, what sets of tools it can't. I wish we could go deeper on that. There's some really fascinating stuff there. They had to take away the step forward tool in order to get it to work correctly, and that's a really interesting discussion. But it works. This is all engineered well, and it works quite well on real problems too.
Yeah.
If you want to see some of that, go stop by the Undo booth. They also have some great videos on YouTube of this. This is really the future of software engineering, and I'm so excited to get to be a part of it with the Undo team. So thank you so
very much. It's been fantastic working with you on it.
Thank you. Whew. I get goosebumps seeing that. I don't know about you all. I think that this is really cool, and it's really going to change the way that software engineering works. So I want to talk briefly about coding with LLMs. And I'm going to skip over the next slide. It's a really cool slide, but I want to get to the interesting stuff that you can actually apply here. And I think this is the mental model right now, at least. I think agents will probably get better, but the mental model right now that I think is very useful for understanding what tasks or approximating what tasks the LLM will do well and which ones it might struggle with is that it's like a junior engineer who's read the whole internet, right? The struggle with very large scope tasks, things that you would normally delegate to a more senior member of your team, like abstraction design or code that's used in a lot of different scenarios, libraries with a diverse set of stakeholders that all have different requirements that you have to balance, right? Keeping all of those stakeholder requirements in its brain and balancing them is like a very large scope task, and it's not something you would give a junior engineer right out of undergrad. No offense to anyone who was a junior engineer. I think I would have been terrified getting that kind of task also. Like, architect the stuff that your colleagues are going to write for the next 6 months. It's not something you should try and give to an agent either, right? But they tend to overperform on highly arcane or obscure tasks that are relatively small in scope. Build systems, source code, repository management, knowing the right incantations to cherry pick 3 lines from one file into another file without messing up your Git history. Like, I have no idea how to do that off the top of my head. I have not used Git once since arriving at Anthropic. Claude does all of that for me. Is there anyone here who would like super miss having to remember all of the like nerdy incantations in Git? Okay, I am at a C++ conference. There's like 3 hands, but and I suspect I would have to say the same thing about who loves writing CMake code. Like, there's probably 3 of you. Yeah. Okay, but like these are the things that you could very reasonably never have to do again, and that's really exciting to me, right? Template metaprogramming. This is a really interesting one. Often very well contained task of like expressing something that often is very compile time checkable, but the difficulty in it is the arcane, weird rules of C++, not necessarily the scope of the project. Compiler intrinsics. Often when you're using compiler intrinsics for something, it's in a very, very specific, well-constrained case. Because otherwise, like, you can't really generalize compiler intrinsics that much, right? Like, let me talk a little bit about some of the ways that you can go about using a model. Like, if you dive in, right in, and say, do my whole project for me, go, you're going to be a little disappointed. You might not be. Like, you might be surprised. But you're going to be a little bit disappointed. And so here's kind of some of the ways you can start ramping up in that direction while still doing your day-to-day job. One of them that's very useful is rapid prototyping. Like, is this even possible in the code base? And how much work would it be, right? And you can often get horrible code quality working version in a few hours doing this. And that will give you some idea of like the upper limit of how complex the problem could actually be, right? And then you can go back and follow kind of the same process, but with better code quality to implement the same thing. And I find that to be very useful. Side quests, I don't know how else to describe this. It's basically like, I'm sitting there handwriting the mission critical code, but there's this like functionality like logging or serialization that I know needs to happen eventually. And I know I'm going to have to go back and write at some point. It maybe touches part of the code that I'm not as familiar with, but it's pretty small in scope and pretty well contained, pretty easy to understand. I will often, while I'm writing my mission critical code, go off into a window to the side, start up Claude, and have it write the thing. Sometimes I'll even just leave a to-do Claude write the function that's being called here, and then explain it, and then have it remove the to-do when it's done. That's kind of a direction. Sorry, I'm saying Claude here. This is really not intended to be an advertisement for Anthropic. I should have made that very clear. I think, yeah, I won't say much more about that, but like that is what I use in my day-to-day, and that happens to be like the word we use as a proxy for agent at Anthropic, and so I slip into that sometimes. Planning and brainstorming. You saw this in the Clang example, right? You actually had a reasonably functionable implementation plan for a switch const expr feature with no exposure to the Clang code base before this, right? It also kind of helps me a lot with writer's block. There were several times where I was making these slides and I was like, what goes here? And it would give me 15 options and I'd read through them and I'd be like, oh, yeah, I really like that direction. And then I'd start, and I'd write something different from what it said, but yeah. Learning and exploration, we already saw that, right, in the demo. Refactoring, boilerplate reduction, modernization, cross-language translation. I think these are all tasks that are quite, tend to work quite well with agentic models because they don't require very large scope understanding of what's going on. It's kind of a maintain the same functionality with a different way of saying it. And the models seem to be pretty good at that. Test generation especially. Again, I don't think most people in this room love writing tests. And this is another example of a place where I skim the tests that the model writes, but I don't always even fully read through the tests. Because I think that is like slightly less mission critical, as long as it's like not making things up. You do have to skim it. But as long as the tests pass, and the code seems reasonable, like I wrote the code, maybe this is a pretty good idea. I know I'm going to get slammed in the comments by people who love writing tests, but like I do think that this is a way to accelerate your software development. Let's talk about best practices for writing code that's going to interact with agents. And spoiler alert, it's basically the best practices for writing code that's going to interact with humans. One of them is that if your LLM keeps guessing at your library interface incorrectly, maybe it's too surprising. Maybe this is an indication that humans will also guess incorrectly at this library interface or what it does. Maybe you're being too cute. Maybe you're using operator overloading a little bit too loosely, right? and it thinks that something's happening when actually something else is happening. If it's guessing the effects of your function incorrectly, it's another good indicator that maybe your function's name is not very indicative of what the function does, right? Maybe your function's signature is not very indicative of what the function does. I would say, like, this is what has really helped me succeed coding with agents, is overthink this principle of least astonishment. When you write code that an agent might read, like, actively think and be creative about coming up with ways that the code could be misinterpreted, and then try and guard against those. If you have to use a comment, do it. If you can come up with a more bland way to say the same thing, the model is probably quite a bit less likely to make a mistake. So some surprising C++ things to avoid. This is like every other CppCon talk out there is going to talk about these kinds of things. We all know these are good practices, even though C++ allows them, doesn't mean you should do them. You're going to confuse people, and if you're going to confuse people, you're going to confuse agents. Yeah, don't be clever with operator overloading. Don't mix owning and non-owning semantics in the same type. Avoid macros. What did I just do? Oh, resume presentation. OK. Avoid argument-dependent lookup. I think this one's especially bad for models because you have the same sequence of characters doing different things in different places. That can be very confusing, and it can be different places even in the same function. That's like, I think argument-dependent lookup done very, very well can be intuitive, but like most people don't. Avoid implicit conversions. Don't do anything important in an implicit conversion function. Use regular types whenever possible, right? This is all best practices of C++, and I'm just restating them here. There's nothing new here. There's nothing specific to agents here, although we can start to look at some of these things and say, oh, I kind of understand why the agent would make the mistake, right? We can look at the ADL and say, oh, it's the same tokens. Of course, it's going to have a little more trouble correlating the behavior to that token, right? And that kind of explains this intuition we've had for a while of why humans get confused by this. But it's not new advice. This is a really, really big one. Prioritize better encapsulation. If you can figure out a part of your code that is very well encapsulated, very well unit tested, that you never have to touch, you can often have have your agent own that code, right? I have several instances where I have a part of the code that I've written 0 of the lines of. I know how it works. It's well encapsulated. I leave it off to the side. Now, like, maintainability of that code is something you really do have to think about. And sustainability of agentic code is a thing you have to think about. Think about the largest that thing could grow to, right? And if that's large, probably don't do this. But if it's well contained and is not going to grow, and you are fairly sure it's not going to grow, think about this. Think about maybe having code that you don't own. Because, spoiler alert, if you become a senior or principal engineer, you're going to have to do this anyway. You're going to have to learn to get very good at this. The agent should be able to reason about the code in isolation as much as possible. Especially avoid code coupling. I think anytime you are making changes and they have surprising effects on unrelated code, you're going to confuse the agent. So err on the side of repeating yourself. This is a little bit controversial, rather than breaking encapsulation and reusing code. My CppCon 2023 talk goes into great depth on this, and I think actually the advice in there applies pretty heavily. Here's the links. Document your code. This is a big one, I think. Comments are kind of more important for agents than they are for humans, because agents do read comments every single time. And more importantly, like, agents can maintain those comments. We do this at Anthropic. You can set up a CI step that asks an agent to verify all of the comments related to the changes in your pull requests and make sure none of them have rotted. It's not completely foolproof, but it's way, way better than what we had before, and I think really tips the scales towards this idea that self-documenting code doesn't rot while comments do is just not, is starting to age, right? I think it's getting outdated. Key takeaway, writing code for LLMs is not that different than writing code for humans, except for that we can start to understand why. Oh, I left 8 minutes. This is better than I thought I would. But this is the talk where I said we geek out about C++ a little bit and what we think the future's going to look like, or what we think a future evolutions of C++ for agents might look like. And I have this kind of category of things that I call two-sided naming. I haven't come up with a better term for it. I've looked for one. If you have one, leave it in the comments, and I'd love to hear more. But it's a broader category of things than just most of the other terms I've seen. The simplest version of this is keyword arguments in Python or many, many other languages, where you actually can say at the call site what the semantic meaning of the argument is, right? Positional arguments don't carry semantic meaning unless you have the declaration in context. And we can start to understand why the declaration might not be in context by chance or whatever, right? And so I think this is a pretty clear win. I said this last night on the Grow the Committee panel. I think this is something we could do in C++. I think that languages that absolutely require this are going to have some very interesting advantages. Like this is the call site in Objective-C. Part of the name of the function is the parameter names. And I think that's actually a really interesting model where you're actually required to state the semantic information there. But more examples that are not keyword arguments. In Rust, when you are going to borrow something, you have to say how you are borrowing it as a reference at the call site in addition to at the declaration. So we know that there is a reference bound to this thing. We know that there's a mutable reference bound to this thing, and it could change, right? And I think that's actually incredibly valuable for the agent that's skimming the code to say, oh, this was called in a way that that variable could change. We have no indication of that in C++, and I think that that's pretty scary. In-out and Swift is another example of the same thing. And I've given all this rationale, but I'll leave it in the slides if you want to go over it. Contracts are a really, really effective way of encapsulating information and reducing code coupling by really explaining the intent of the boundaries of the function in its declaration. And I think that this is something that can very efficiently and maintainably and verifiably use context windows more effectively. I'm not going to go into all the details here. There is a caveat, right? So these are all things that make humans more effective at programming. There's a lot more I could go into here. There is the two-sided naming version of contracts where you actually have to opt into the contract at the call site and acknowledge it, so you wouldn't even have to go retrieve the declaration. These are like features in programming languages that have never gained a lot of momentum because they're too complicated. And so that's this caveat, right? Is that like if the learning curve is not too steep for humans, then, or if the syntax is not too obscure or arcane for humans, then these things will benefit humans. The problem in the past with like the reason why this is not HaskellCon is because the learning curve is pretty steep and the syntax is arcane and the effects are arcane and they're difficult to reason about. But remember, agents are good at that. And so I think that's a really interesting thing to keep in mind as we move forward. I'm going to skip this so I get to my summary slide because I really want to drive home a few points, and then I'll have a little bit of time for questions until they kick me out at least. So coding agents are tools that take some time to learn and use. They generate output based on, I literally added this slide this morning because I really want to drive home some of these points. Clearly didn't read it. They generate output based on input, and the quality of their output depends on the quality of their input. The context window is all of the space that you have to give input to the agent to control your tool, use it effectively. When I hear people say LLMs can't do this or LLMs can't do this yet, I want to correct them and say it's much more likely to be accurate to say I can't do this with LLMs or I can't do this with LLMs yet. I've been operating kind of at the forefront of agentic development for the past 6 months. Or 7 months now, I've gotten the opportunity to work with a lot of people using this at very large scale to build entire startups out of this technology. And it is a skill that takes a long time to learn. I have gotten significantly better at it over the past 7 months, but I am not there. I'm not perfect yet. But this is, if you learn one thing from this talk, I want you to think about LLMs this way, right? This is a skill that you have to learn. It's going to take some time. It's not going to work right away. Remember this notion of coding agents are like junior engineers who have read the whole internet. Or if you're a junior engineer, think about it like an intern. If you ever had an intern, what kind of project would you give to an intern, right? If you're an intern, hey, welcome to C++. Welcome to CppCon. You're way ahead in your career going to conferences like this. Good job. Yeah, and it's worth taking the time to learn intuitively what coding agents are good and bad at. And refine this kind of heuristic of junior engineers who have read the whole internet. Careful and intentional design can really accelerate your development process. Encapsulation is good, code coupling bad. Good documentation is going to pay off more than ever. The future of programming languages and software engineers is really going to be anything but boring, and I'm just super excited to be alive for all of this. So thank you all. I'll take questions. Yeah. Sorry, I ran right up to the edge. So if your question doesn't get answered and you're in line, talk to me in the hallway, post on Discord. Hey.
Hey. Okay, cool. So I look at using an agent like doing pair programming. But when I work in a larger team, it's sort of unusual because I'm working with an agent, someone else is working with an agent, we're sort of working things together. Any thoughts on like how you can use agents in a group effectively? Like to not confuse the context, it's just one of those ways like having a three-way conversation, like making sure I hand things off. What's your thoughts on that?
Yeah, I think there are a number of directions we can go to this. I didn't really get a lot of opportunity to talk about how memory works in agents. I would have loved to, but yeah, memory is the general topic here, or in-context learning, where you could take some information from one agent and kind of use it to build up context in another agent. Specifically in the context of teams and enterprise settings, we are working on some stuff that I can't talk about, but watch this space. We've really kind of started to double down on this in the past month. So.
Hi, Daisy. Fabulous, eye-opening talk. I had a ton of questions. I picked just the top two. So first of all, you haven't talked about safeguards that might be in place for all these Skynet unknowns you've mentioned. And second thing, do you think we'll still be needing static checkers?
Oh, that's a good one. I think static checkers, so I'll answer the second one first because that's easy. I think static checkers are an extremely useful tool for the agents to use. I think they need the ability, I didn't even get to go into talking about hooks and LSP integration and things like that. I think those are very high on my list of things that I really want to figure out. This is part of this process of going from ED to VI to an IDE for the agent, is figuring out what kinds of environmental feedback signals can we give it to improve its output passively. And I think that's a really open area of research. Safety, I'm not going to pass on. My whole company's mission is focused entirely on safety. I think the first thing I'd say is write mission critical code yourself. There, in the Claude Code source code, there are a few files that the vast majority of us do not allow Claude Code to write. So we really do practice that. Write your mission critical code yourself and understand the boundaries of the amount of harm that can be done.
Thank you.
Hey, Chris.
Hey, Daisy. Hey, Daisy. Great talk as always.
Thank you.
I was wondering if you could comment or speculate on maybe the use of diffusion to
I wondered if you were gonna ask
unleash
that.
maybe some of the limitations of the sequential token generation.
I am pretty bearish on text diffusion. I actually think I'm a little bit bearish on image diffusion long term. This is a much longer discussion, but I think that the main takeaway there is that we are actually seeing models move, multimodal models move away from diffusion-based generation of images because the token-based generation, iterative generation looks more promising long term. And the other thing I would mention in that context is the bitter lesson. I don't know if you're familiar with the bitter lesson, but if you Google bitter lesson AI, I think that might give you some idea of where I would go with this if I had more time to answer the question.
We should talk later about
We should definitely
BLAs.
talk later. I'm excited to talk about how this works with robots too. So, hey.
Hi, thanks. This is a great talk, Daisy. So I had a question, or maybe related to one of the slides where you mentioned that comments are really important in code. But it generally happens that comments keep on like being static, but the code changes over time. So
Yep.
how good are these agents in actually kind of detecting these kind of differences between comments and know that the source of truth is always the code?
Very good. We use them and rely on them and regularly check their outputs. And our CI process has basically made this problem go away. Like pretty much none of the comments in our code base rot. So, and we've done audits of this, and we are very convinced that this is something that agents are very good at.
Thank you.
Can I take like 3 more questions? Do I have time for that? Go for it.
Hi. One question I have is, I want to connect 2 dots. So you said that the ground-shaking realization with thinking was to just put that little bit of pre-prompt of like, think step by step. That's all it takes. And then the other thing you said was the limiting factor is tooling. So combining the 2 together, have you tried to ask it what better tooling would it need? And if you tried, has it failed? Or if you didn't try, do you think it would even work? And do you have an intuition of why it wouldn't work?
Yes, I have asked it. In fact, that is when I got hold of the Claude code base, the first time when I got it to Anthropic, which was at the time called Claude CLI, which was before we'd released it. The first thing I did was to run it in its own code base and ask, what tools do you want that you don't have? It came up with some good ideas, and in fact, one of the tools that I can't talk about, but that it suggested at the time, just made it into the code base in August and is making a huge impact on how our team does things. So yes, this does work surprisingly well.
I guess the next step would be to give it a tool to write a tool, and then it can like auto-create tools.
That is more or less the thing it suggested in March when I tried this, or February when I tried this. So yeah.
Okay, thank you.
Hello. So one of the things I noticed, and you briefly touched on how this might be suboptimal, but a lot of this newer innovation is very new to me, and I noticed that almost all of the intermediate formats are just plain text. Like you were showing the XML file and the human program call and response as just plain text. Specifically for those complicated XML files that you were showing, you were talking about how demanding it is to have to generate those so precisely. But I wonder how much of the power is being wasted on just XML syntax. Do you think there's room in the future for it actually just generating more structured output instead of plain text?
Yeah, I'm loving these questions because these are exactly the things that people are thinking about in the field, and it is perfectly illustrative of how a lot of this field is low-hanging fruit right now. Yes, there's this thing called constrained sampling, where you could, for instance, put the schema in the in line with the sampling, and when you would actually sample for temperature, if there's something that is not allowed by the XML schema, you just throw it out and you don't have it as part of your sampling. Does that make sense?
Oh, okay.
Yeah.
So it's
it's
still
not
generating a text file, but it would be doing so differently.
Yeah. So you're not making the model have to think that much about it.
Interesting. So so you're still doing text file, but giving it more structure to create it easier rather than just not using a text file.
Yeah. And I think there are probably other things that we can do in the future that we haven't figured out yet. Like once we invent VI, I think would be really cool. I can take one more. Can I take one more?
Really appreciate the talk. So I've been reading a lot of papers lately about alignment, and there's a lot of proposals for monitoring chain of thought during like the reinforcement learning process, which is kind of like a no-no. But I asked a lot of the different models, do you think that your chain of thought is being actively monitored? And all of them are like very vehemently saying, no, my chain of thought is definitely not being monitored. But I'm curious, when those papers start coming into like the pre-training, like the training data, do you think they're gonna be like less sure and maybe like try to obfuscate their chain of thought?
I learned the answer to this last night. So this tells you something about how quickly the field is evolving. Most of that, the teaching the model that its thinking is concealed, and so it doesn't need to do that much polish on its thinking. Most of the training to get it to understand that is done in reinforcement learning and not in pre-training. And so even if it is in pre-training, we pretty heavily teach it during reinforcement learning that this is not something that the user sees, because we score on the part that the user does see, and we treat it as a scratch pad. We have various mechanisms for doing this. I'm not going to get too much into it because reinforcement learning is something to be very careful about. But the public answer is that yes, even if this made it into the pre-training data, it would probably get removed in reinforcement learning, especially as I expect to see more reinforcement learning in the future relative to the amount of pre-training. But I do think that's a really interesting question, and we don't really know for sure. And I think it kind of thinks that it's not being monitored, but I don't know that it understands what that means, if that makes sense. But this is me completely conjecturing. So yeah.
Thank you.
Thanks for your question. Thanks everyone for listening, and yeah, thanks for the opportunity.